Hello everyone. After we talk about the magnetic field and magnetic circuit details, let's solve an example how we will calculate the magnetic circuit parameters. So we have a magnetic core figure with the dimensions and some important parameters. Now we will try to obtain the equivalent circuit to be able to easily analyze such a figure. How we will start, the first step should be how many sources and how many reluctances we need to use to describe this figure as equivalent circuit. So the source part, I think it's easy because according to your supplied windings, you can determine the number of sources. So in this figure, we have only one source on the left leg, which is located. And according to current direction, also we can determine the source polarity. Source polarity will not be important for such a system because we have single loop, single way for the flux, but for the complex versions, we need to determine in some examples, in some systems, the polarity of the source. So because of this, let's start by starting how we will decide flux direction. So our current direction is given in this way. So if you hold the core with your right hand four fingers, except your thumb finger will show the upwards. That means the source positive sign must be located like this. And the source value, as we discussed in previous lectures, it must be equal to N times I, total magnetomotive force. Okay, after we decide that, we need to consider the reluctance or reluctances. How we will decide for single loop system, again, it is simpler. We should start with the reluctance equation. As we discussed, reluctance is equal to mean path length over permeability times cross-sectional area. So if we have single loop, we can continue our analogy with the electric circuits. The denominator will be important. Why? Because we will add, if we have more reluctances, their denominators must be added, must be equal to be able to easily add them. Okay, in the denominator, we have two parameters, the permeability and the cross-sectional area. So in our figure, we don't have different permeability value. We have single type of material and there is no air gap. So that means the permeability must be equal in each point of this core. What about the cross-sectional area? So in this figure, we draw a two-dimensional picture, but it's actually three-dimensional system. So to be able to calculate its cross-sectional area, we must multiply the width of the leg with the depth of the core. So because of this, we must check the widths of the legs. So for example, in here we have 10 centimeters. In here we have 5. But in this part, we have 15 centimeter legs. That means because of these differences between the width of the legs, we have to use at least 3 reluctances to be able to describe that figure because of these different values. So we must use 3 reluctances. Let's try to clarify them. How we will clarify? For example, we can separate them with different names. For example, our 15 centimeter width can be called as R1 and the other one, for example, for the left side, let's say we have R2, and for the right leg we can call it as R3. So according to our reluctances, we have 2R1 in one loop. We have R2 and R3. After we draw the magnetic circuit, now we can calculate them. Calculate our reluctances to be able to calculate the parameters of the circuit. So let's start with 2R1, 15 centimeter width parts of the core. So 2R1 must be equal to 2L1 over nu times A. So in the calculation of the reluctances, the cross-sectional areas will be also different. So because of this, let's call it as A1. What is L1? For the mean path length, we are taking the dimensions for the legs, but for the corners, we are taking only half of them. So, for example, for R1, we have, first of all, 5, which is half of 10. Then here we have 20, and the last one will be 2.5, which is half of 5. So still we have 2 because we have 2R1 in our circuit. And our mean path length dimensions are 5, 20, and 2.5 from left to right. And we must convert to meter. For the denominator, we have our first parameter is nu, which is permeability. And permeability means which is the multiplication of relative permeability and the free space permeability. So relative permeability is given as 800 and relative permeability it's a constant as 4 pi 10 to the minus 7. The cross-sectional area, so we are calculating the R1. For R1 section, the width is 15 centimeter and the depth is also given, which is 5. So 15 times 5 must be converted to meter square. So from here, 2R1 can be calculated as 72.9 kilo ampere turn over Weber. Okay, let's continue with R2, with the left leg reluctance. For R2, similarly, we have its mean path length and cross-sectional area. For this part, if we start from the left corner, left upper corner, our values will start with 7.5 centimeter, which is half of 15. Then we have one more 15. And the last part again must be half of 15, which is 7.5. Again, the unit conversion must be applied. For the denominator, as we say, there is no different permeability for this example. 800, 4 pi 10 to the minus 7, again must be in our expression. For the cross-sectional area, when we check R2, our width is 10 centimeters and the depth is 5. And again, we have the unit conversion. So 59.7 kilo ampere turn over Weber will be the second reluctance. What about the third one? And it will be the last one for this example. For R3, we have the same mean path length with R2. There is no difference. They are starting from the up and down with same dimensions. So because of this, for R3, we can use L3 over nu A3 equation. And same values we must write because if you start from the up, it will be half of 15, 15, and half of 15 again. For the denominator, only the cross-sectional area will be different. According to given values, the width for this part is 5 and depth is also 5. So we have 119.4 kiloampere turn over Weber. Now we examine the figure and we obtain the parameters in the magnetic circuit. So that means we can continue with the magnetic circuit after that. How? We can find the total equivalent reluctance for this circuit. So these are connected in series. And for the reluctances, also we can follow the series connector resistances equation. Because of this, our equivalent can be calculated as 2R1 plus R2 plus R3. So total reluctance, equivalent reluctance for the circuit will be 252 kiloampere turn over Weber. So we have the source plus minus Ni, and we have an R equivalent here. So we have very simple circuit now. We can calculate the unknown parameter, which is I. So for the I, again, we can use our similar expression with Ohm's law. That means total magnetomotive force, which is Ni, must be equal to phi flux times reluctance. So what we are trying to calculate? The current. So our expression will be phi r over number of turns. So for the circuit, we will use our equivalent reluctance for the total flux. So the flux is given as 5 milliweber, and the equivalent reluctance has been calculated as 252,000 because of kilo, and the number of turns as 500. So from here, you can find the current as 2.5 amperes. So that means if you want to produce 5 milliweber flux inside the core, according to given dimensions and properties, you must apply 2.5 amperes to the winding. Okay, so in addition to current flux calculations, we can calculate the magnetic flux density for such a system. How? Magnetic flux density and the flux relation can be used. B is equal to phi times 5 over A. So what we want to calculate? For the density, instead of single flux rotation inside the magnetic core, our cross-sectional areas will be important. So if we have different cross-sectional areas in that parts of the core, the magnetic field densities, because of the density term, it must be different. So for example, for the top leg, if we calculate the magnetic field density, flux 5 milliweber, and for that part, for the top leg, we defined as R1, and R1 cross-sectional area includes 15 centimeter width and 5 centimeter depth. So 15 times 5 must be converted to meters square, and from here you can find as 0.67 Tesla. So for each magnetic field density, we can calculate according to its specific cross-sectional area. Okay, Thank you for watching.